All right, as you can see, these are the problems with colligative properties. So first of all, just to do a little definition here, colligative properties, what those are properties that are affected by the concentration of the solute. Now, something here that's important is that it doesn't really matter what solute you're using. It just matters how concentrated it is. Okay, the boiling point elevation, what that is it's a rise in boiling point due to dissolved solute. And then similarly, freezing point depression, that's a lowering of the freezing point due to dissolved solute as well. Okay, then we've got some equations here. It says delta TF equals I times M times KF. Okay, so that's going to tell you how much the freezing temperature is going to change. For water, I've given you the value of KF. It's just a constant there. And then we've got the boiling point equation, which is right next to it. So change in boiling temperature is I times the molality times Kb. This I here is called the Van 't Hoff factor, and you can think of it sort of like the number of pieces that something's going to break into. And so really what you're thinking about here with the Van 't Hoff factor is if it's ionic, it's going to break into however many atoms are in the ion. So NaCl would break into 2 pieces, CaCl2 would break into 3 pieces, Ali3 would break into 4 pieces, things like that. And so however many pieces there are for the ion, it's going to break into it. For something that's covalent, for something that just has nonmetals in it, the Van 't Hoff factor is going to be 1. And so it's sort of important that you understand how to get that Van 't Hoff factor. Molality, that's the moles of the solute over the kilograms of solvent. So this should be an A here. All right, so we're going to go through and do a few practice problems here, and then I'll go through the main sheet. So this first one here starts off, it says you've got sodium chloride, and we're wondering if a chef's adding this salt or sodium chloride to a pot of water, how much faster it is going to boil, or sorry, how much hotter it's going to boil. And so what we get here then, you have to realize if it's NaCl, if it's just normal salt, then the Van 't Hoff factor is going to equal 2. That'll come into play later. We start with 25 grams. We need to get to molality, which means we need to find the moles of salt. Okay? To do that, we need to go from grams to moles using the molar mass from the periodic table. So we start 25.0 grams of NaCl. Then, if you look up on the periodic table, you can find 58.44 grams in 1 mole. You multiply those, you get 0.428 moles. All right, now we can calculate molality. Molality is the moles of the solute, so that's that 0.428 over kilograms of the solvent. In this case, it's just 1.0. That ends up giving us 0.428 again because it was just divided by 1. Now we're in units of molal. So now we're going to calculate the change in boiling temperature. For that, we say change in boiling temperature equals I times molality times your boiling point constant, Kf. Whoops, Kb. All right, so now we'll multiply them. That's 2. The molality is 0.428. And then the constant there is 0.51, and this is for water. So every time you're using water as your solvent, that's what it will be. You go through, you get 0.437 degrees Celsius. Now this isn't your final answer. This is just telling you how much the boiling point is going to change. The normal boiling point for water is 100, and so if it's going up, it's elevated, it's boiling point elevation. then we're elevating it by 0.437 degrees Celsius, which means our new boiling point, our new boiling temperature is going to be 100.437. So we're just adding 100 to it because the normal boiling point is at 100, and we're changing it by going up by 0.437. And we should have degrees Celsius here. All right. Number 2, it says freezing point, same solution, and so we don't have to do all the calculations that we did originally because that was just to get molality. So we can jump right to delta TF equals I times M times KF, which equals 2 times, again, 0.428 times our KF, that's negative 1.86. We multiply all of those together, we get negative 1.59 degrees Celsius. All right, so this is the change in temperature. It's going down by, the freezing temperature is going down by 1.59. Now the normal temperature is 0, and so if we're at 0 and then we go down 1.59, we actually end up at negative 1.59. So it seems like it's the same number here, but that's just because the freezing point for water is 0, and if you change from 0, you're going to get whatever number that changes. So, yep, it's negative 1.59 degrees Celsius. Problem number 3 here, calcium chloride, substance placed in the streets. So this is what you're using to melt normal ice on the sidewalk. It's what you go and buy at the store to melt ice. It says that they're going to put it in a spray pump here, and it's asking how much it changes the freezing point of water, actually rather what the new freezing point would be. So our substance that we're talking about here is CaCl2, which is calcium chloride. The Van't Hoff factor for that one is 3. And so we're going to do the same sort of steps as we did before. We start off with the mass that they gave us. So we've got 790.5 grams of CaCl2. If you look up on the periodic table, you can find the mass of CaCl2. It's 110.98 grams in 1 mole. Go through, calculate that, you get 7.12 moles. We're going to plug that into the molality equation. So molality equals 7.12 moles over 0.450 kilograms. Notice here, it was given in grams. I had to convert it to kilograms because that's what the molality equation says. So then you calculate that, you get 15.8 molal for the concentration there. So then we know change in boiling temperature or freezing temperature equals I times M times the freezing point constant. And then Van't Hoff factor I said is 3 because CaCl2, calcium chloride, is an ionic substance. It's going to split into 3 pieces. 3 times 15.8 times negative 1.86. All right, multiply those together, you get negative 88.16 degrees Celsius. All right, and then for this one, again, it's freezing point. This is the change in temperature. The normal is 0, so your freezing temperature is going to equal negative 88.16 degrees Celsius. On to the next page here. So quite a few problems. It starts off pretty easy though. We're given just moles here and kilograms, so you can calculate molality right away. You don't have to start with the grams. And so we know molality is going to equal your moles of your solute. That's 3.68 moles over your kilograms of the solvent. That's 2.5, which is going to give us 1.47 molal. Then we're going to plug it into the delta TF equation. So we know the freezing temperature here is going to change by I times M times KF. I in this case This is sucrose, if you see the formula there, C12H22O12. Those ones are, that's all covalent, okay? It's all nonmetals. And so this one's only going to split into one piece, or it's going to stay as one piece, however you interpret that. And so our Van 't Hoff factor is 1. The molality here is 1.47, and the freezing point depression constant is negative 1.86. So we go through and we multiply all that out, we get negative 2.73 degrees Celsius. Okay, so then if we're doing this, we know that our freezing temperature, our new freezing temperature, again, because it's normally 0, and it's changing by negative 2.73, is going to be negative 2.73 degrees Celsius. Problem 2, it says you got 5.76 moles of sodium fluoride. It's dissolved in 3.62 kilograms of water, and it's asking what the change in the boiling point will be. So this one here, our Van 't Hoff factor is 2 because it's sodium fluoride. NaF is an ionic substance. It's going to split into an Na atom and an F atom. So we're going to start here and say the molality equals our moles, 5.76, over our kilograms, 3.62. You divide those, you get 1.59. Then we have our change in boiling temperature equals I times M times our constant for boiling, which equals 2 times 1.59 times 0.51. Okay, multiply all those out, you get 1.62 degrees Celsius. Now this is the change in temperature. Our normal boiling temperature is 100. So here, our temperature for boiling is going to equal 101.62. So normally it's 100. It changes by 1.62. So we end up 101.62. It's going to go up by 1.62 degrees Celsius from the normal. Number 3 here, we've got potassium iodide. Potassium iodide is ionic. So our I here is going to split into 1 potassium and 1 iodide. So our I is 2. We've got 30 grams here it's given us. We've got to convert that to moles right away. So 30 grams all right, and then if you calculate the molar mass, you get 166 grams in 1 mole. You multiply those, you get 0.181 for your molality, for your number of moles. And then we'll have our molality equals 0.181 over 1.75 because it said 1.75 kilograms. You divide those, you get 0.103 for your molality. Then we know the change in the freezing temperature equals our Van 't Hoff factor, which is going to be 2 times our molality, 0.103, times the freezing point constant, negative 1.86. All right, multiply all those together, you get negative 0.383 degrees Celsius, and so that means our final freezing temperature equals negative 0.383 degrees Celsius. Problem number 4, we're starting here, 30 grams again, this time 30 grams of NaCl. So we start here, 30.0 grams of NaCl, very similar to the last problem. In this case, 58.44 is the molar mass. You multiply those, you get 0.513 moles. Our molality then is going to equal 0.513 divided by the kilograms, 3.75. All right, and you get 0.137 molal. Then, next step here, we're going to say change in boiling temperature is going to equal I times the molality times your boiling point constant, which equals 2 times 0.137 times 0.51, and we get for that 0.140 degrees Celsius. Normal boiling point for water is 100, so our final boiling temperature is going to equal 100, and then it changed by 0.140, so 100.140 degrees Celsius. Number 5. So this one says we've got a 3.6 molal solution. It wants us to calculate Kf. It tells us the freezing point was depressed by 0.851 degrees Celsius. On this one, I didn't tell you in the problem, but you should assume I equals 1 because it doesn't tell you what the solute is, so you don't know what it would be, so we're going to say I equals 1. So you just plug this in. Change in freezing temperature equals I times m times Kf. And so the things that we know the change in freezing temperature is 0.851. I said just assume that's 1. The molality is 3.60. All right, and Kf is our unknown here. So you solve there, you get Kf equals negative 0.236 degrees Celsius per molal. Number 6, we're going to assume here again that I equals 1 because it didn't tell you what I was. So it's very similar, except this time we're dealing with the boiling equation instead. So change in boiling temperature equals I times m times Kb. In this case, it was 1.62 was our change in boiling temperature, which equals 1 times 5.70 molal, all right, times our Kb. You solve that for Kb, you get Kb equals 0.284 degrees Celsius per molal. Alrighty. Number 7. This one's a little bit longer. So it tells us CAM4 has a molal freezing point depression constant of 5.95 degrees Celsius per molal. So that's telling us how much the freezing point goes down. This should actually be negative here. All right? This should be a negative 5.95 because it's how much the freezing point is depressed. So later on we'll plug it in that way. And then what we're doing is we're dissolving this dimethyl ether into the camphor. And so it tells us kind of the amounts. This is not that much different than the problems we've been doing in the past, except for instead of water this time we're using that camphor. So what we'll do here, we've got to get this to moles to start off with. It says that we've got 10 grams of dimethyl ether, so 10.0 grams of C2H6O. And if you calculate that, you get 46.08 for your grams, your molar mass for 1 mole. Calculate that, you should get 0.217 moles of dimethyl ether. Then we can calculate the molality. Molality is 0.217 divided by 3 kilograms, so divided by 3. which in this case equals 0.0723 molal. Then the next thing we got to do, we got to calculate the change in freezing temperature. So delta TF here equals 1. Okay, I'm going to say the Van 't Hoff factor here is 1 because our substance that we're dissolving here is this C2H6O. And all of that is nonmetals, it's covalent, it's not going to split up when you put it into solution. So we're going to say I equals, oops, that should say I equals 1. It's just going to be one piece when you put it in there. So I is 1, the molality 0.0723, and then that constant there, that Kf of negative 5.95, and I get negative 0.430 degrees Celsius. This is negative because it's freezing point depression. It's going to go down. We don't know the normal freezing point of camphor, but if you did, you would just subtract 0.430 from that. So let's say the freezing point of camphor was something like 40 degrees Celsius. So 40 minus 0.43, that'd be 39.57, okay, would be the new freezing point. And so you just take whatever the normal freezing point is, you subtract 0.43 from it. But again, in this one, it just asked us for what the change was, so this is our final answer here. Okay, just a few more problems here left on this last page. For number 8 here, what we've got here, it says you've got a solute dissolved into diethyl ether, and then it's asking us to find what the concentration is in molality. And so this is another one where they probably should have told us what substance we were having, or they should have told us what the Van 't Hoff factor is. I'm going to assume it's 1 because they didn't tell us what substance we were dealing with here. So anytime I don't give you a substance, assume that I equals 1. So we know that the change in freezing temperature here is going to equal to I times M times Kf. All right, and then the things that they gave you here, they told you that it changed by 4.75 degrees, and since it was decreased, we're going to say negative 4.75 for our change. Equals Van 't Hoff factor of 1 times our molality, that's what we're trying to find here, times our Kf. It tells us there that the Kf for diethyl ether is negative 1.79. Okay, so you can solve this for M, and you get that the molality is equal to 2.65 molal. Problem number 9 here. Similar problem. What we're doing here, we're going to try and find the molality. It's NaCl because it says it's salt water. So we know that I equals 2. We're going to deal with the change in boiling temperature equals I times the molality times your boiling point constant. All right, so then we know 2.5, that's our change in temperature, equals the Van 't Hoff factor of 2 times our molality times 0.51. Okay, and from that you find M equals 2.45 molal. Number 10, so what we've got here, we've got glucose. It says it's going to be dissolved. Because it's glucose, that's C6H12O6. All of those are nonmetals. It's a covalent substance, so it's not going to spread apart into pieces when you dissolve it. So for this one, I just equals 1. It's asking us to find the new boiling temperature. So in order to do this, we need to figure out how many moles of glucose we have there. So we're going to start 10.8 grams of glucose. The molar mass of glucose, if you add it up on the periodic table, is 180.18 grams for 1 mole. Multiply those together, you get 0.0599 moles. Next, we can calculate the molality. Molality equals that number of moles, 0.0599, divided by the number of kilograms. In this case, it's 3. And that's going to give us 0.0200 for our molality. Then we can plug it into the freezing point equation. So change in freezing point equals Van 't Hoff factor 1 times the molality, 0.0200, times the constant here for water, 0.51 is our Kf here. All right, and so, this is boiling point actually that we're talking about here, but yeah, 0.51 is what it is, so delta TB is actually what we need here. Multiply those together, and we get 0.0102. Now, since we're talking about boiling, the normal boiling point is 100 again, so the boiling temperature is going to be 100 plus that 0.0102, so I get 100.0102 degrees Celsius. Last problem here. So this one's talking about dissolving naphthalene into benzene. Benzene is going to be our solvent here. Naphthalene is going to be our solute. We have to figure out how many moles of naphthalene we have. 3.86 grams. The number of grams in 1 mole is 128.18. That comes from the periodic table. Grams for 1 mole. Okay, go ahead and calculate that. You get 0.0301 moles. Then we know the molality equals the number of moles, 0.0301 moles, over the number of kilograms. This is it's 56 grams, so we've got to convert that to kilograms. It's 0.0560. You calculate that, you get 0.538 for the molality. Then we're to calculate the change in boiling point, so change in temperature boiling here equals I times M times KB. All right, we know 1.52 is our change in boiling temperature because it told us that. Van 't Hoff factor, this substance here, C10H8, that is covalent, so the Van 't Hoff factor is going to equal 1 in this case. So 1 times our molality, 0.538, times our Kb. Go ahead there, do the algebra, solve for Kb, and you get Kb equals 2.83 degrees Celsius per molal. So I know that this is a long assignment and a long video. Lots of different ways I can ask you questions about that. Just make sure that you understand all of this. And there shouldn't really be anything other than this on the exam. So, make sure that you're good with this and you should be good for the exam.